Okay. So thank you everyone for joining this great conference, and there is a various topics which involve different subjects. So today I'm going to present about my research topic, which is enhancing drug loading of phenytoin into nanoemulsion via hydrophobic ion pairing and its potential to prevent in vitro precipitation issue upon serial dilution at blood pH. So first of all, I would like to give some brief introduction about what is ion pairing. Ion pairing is a partial association of oppositely charged ions, where long-range electrostatic forces between two ions, between electron charge density of two ions, cation and anion, they come closer and they make the charge neutral. So as you can see, there are two different ions and they are joining with each other and make a contact ion pair or different type of ion pair. This ion pair mostly work on a Coulomb's law, where forces is kind of inversely proportional to the dielectric constant of the medium. Other than long-range electrostatic forces, hydrogen bond and dispersion forces also plays a role in formation of ion pair at some extent. So in case of, if we use hydrophobic counterion, it makes the ion pair hydrophobic and which can precipitate out in aqueous medium. The overall ion pair, it's just the combination of electron charge density of cation and anion, and they come to closer on at only certain period of time. But in some solvent, they can easily dissociate. So overall, it does not change the molecular structure of the drug, but it just combine with each other at certain time period. So for that reason, there is no regulatory documents needed if we are using the drug in ion pair formation. So for ion pairing formation, I am using my drug, which is Phenytoin. It is my model drug, and the Phenytoin has a very poor solubility, around 20 microgram per ml, and it is BCS class 2 drug. The pK of this drug is 8.21. So as you can see here in the graph, that below pK, the solubility of phenytoin is very low. However, when we go above pK, as pH increasing, the drug solubility increasing, and it shows around highest solubility 56 mg per ml at pH 11.63. However, the drawback of this pH solubility profile is when the pH goes down, the drug get precipitate out. So there is a commercial IV solution is available in the market from since a long time. It called dilantin solution, where pH was adjusted to 12 and the 40% propylene glycol and 10% ethanol was added to obtain desired solubility. The drawback of this formulation is that because of this steep pH solubility profile, upon dilution, in vivo or in vitro, because of the pH change, the drug precipitation occur, which cause the side effect at injection site reaction, like itching, redness, phlebitis, or sometimes it happens the hemorrhagic necrosis of the tissues. So to make the ion pair with this phenytoin drug, I have used the CETA counterion, which is hexadecyl trimethyl ammonium hydroxide. CETA counterion is quaternary ammonium compound, always a positively charged and independent on pH. It is also act as a cationic surfactant, and it has a long hydrophobic alkyl tail. So the hypothesis of my research is that the anionic drug phenytoin is kind of interacting with the cationic nature of this CETA counterion and make an ion pair, and this hydrophobic alkyl tail kind of interacting with the whole phenytoin and ion pair and exclude the water from the contact of this phenytoin and make the whole ion pair in a hydrophobic form. So the hydrophobic ion pair formation I have made by using shake flask titration, where certain amount of counterion was added into drug water slurry. As the drug is very poorly soluble in the water, the cationic surfactant is first of all try to dissolve the drug into the aqueous media, and in the same time it is also making the ion pair complexation, and at certain drug counter ion ratio, this ion pair complexation is forming and it precipitate out in an aqueous media. So this solid residue were collected and dried and confirmed through the FTIR, XRD, and NMR. And based on that data, it shows that the counter ion and drug is interacting in 1-to-1 stoichiometric ratio. So further characterization of this ion pair was done using melting point characterization through hot stage microscopy, where phenytoin melting point was observed around 305 degrees centigrade, while the ion pair which we prepared was observed around 150 degrees centigrade. That means by making the ion pair of the drug, we can reduce the melting point of the drug by 150 degrees centigrade. Another characterization was done using aqueous and oil solubility. Phenytoin has a very poor solubility, around 23 microgram per ml, while HIP, I didn't find any solubility into that water. That means it become like purely hydrophobic in nature. The another thing I have tried is oil solubility, where I choose the castor oil to understand the solubility. The phenytoin has a solubility around 4.5 mg per ml in the castor oil, while HIP shows 10 times, 8 to 9 fold higher solubility in the oil, which is more than 40 mg per ml. Log P of phenytoin is 2.5, while HIP has log P, I would say, infinite, because there is no partition was found from octanol to water. So to make the nanoemulsion formulation, I have screened the oil first by using different oils like soybean oil, sesame oil, olive oil, MCT oil, and castor oil. And as you can see here, the castor oil has in castor oil, the phenytoin has around 4 mg per ml of solubility, while HIP has a higher solubility around 40 mg per ml. And this high solubility of in the castor oil due to the high resinolic acid content of the castor oil. In castor oil, it is a 85 to 90% of resinolic acid content, which can make a hydrogen bond with the solute and solubilize the more drug in compared to the other oils. So I have selected castor oil for my nanoemulsion formulation. I also tried different lipophilic emulsifier as a soil lecithin, antioxidant as a D-alpha tocopherol. I use polysorbate 20 as a hydrophilic surfactant, glycerol as a tonicity adjuster, and water. So to understand the solubility in PS20 solution, I try first, like I have added phenytoin and HIP complex in a different concentration of PS20 solution. And as you can see here from this graph, that phenytoin has a very poor solubility compared to the HIP complex. And the pH of that solution is around 5 to 7, while HIP has a higher solubility in the surfactant solution. So as PS20 concentration goes up, the solubility of HIP is going up. And that could be due to the mixed micelle formation of cationic surfactant as well as polysorbate 20. So this one is the like surfactant drug solubility in the surfactant solution. But my original formulation, I am adding drug into the oil phase and then adding this hydrophilic surfactant to make the emulsion. So the main criteria for my emulsion is to understand how the drug is staying into the oil phase when we added the PS20 solution as a hydrophilic surfactant into the aqueous phase. So I have done the another study to understand like how that behaving, how the drug is leaching from oil phase to aqueous phase. So what I have done is I have added phenytoin and the HIP into the oil and then add different concentration of PS20 solution to see how the drug is behaving. So as you can see here, phenytoin solubility does not change much. It is similar to the actual solubility in the PS20 solution. However, for HIP, it shows very poor solubility, means there is no or very less transition is happening from oil to aqueous phase. So overall, this experiment shows that if I incorporate my drug into the oil phase, it will most likely stay into the oily phase and will not transition from oil to aqueous phase and precipitate out. And this is could be due to the high log P value of this ion pair complex. So I have prepared my formulation by having a different concentration of HIP emulsion. I make a phenytoin emulsion with the 4 mg per gram considering solubility, and I have make HIP emulsion of maximum 40 mg per gram of considering phenytoin solubility in castor oil. The nanoemulsion formulation was characterized using zeta potential. As you can see here, the placebo and phenytoin shows negative zeta potential, and that could be due to the lecithin component which is present into this nanoemulsion formulation. However, in HIP emulsion, which can show the higher zeta potential, around 30 to 40 millivolt, and that could be due to the cationic surfactant which is present into the HIP complex. So the complex has already a cationic surfactant and which can increase or which can plays a role in oil water interface and increasing its zeta potential. It is also known that if the zeta potential of the nanoemulsion is higher than plus 30 or lower than negative 30, then the emulsion is stable. So overall, it found that HIP emulsion shows more stability than the phenytoin emulsion. However, in 1 month 5C data, it does not show much. It does not show significant change in zeta potential value. Another characterization was done using droplet size distribution and polydispersity index. The droplet size distribution is showing that all the emulsions are around 250 to 300 nanometer range, which is acceptable for nanoemulsion formulation, and PDI value below 0.5 shows the emulsion is very homogeneous. Another characterization was done for this emulsion is pH measurement. The placebo and phenytoin shows around neutral pH, while HIP emulsion shows the higher pH, like basic pH, and that could be due to the oil-water interface. There might be a cationic ion is present from theta counter ion. Here, I would say 1 month stability showing some reduction in the pH, and that could be due to the oxidation of polysorbate or lipid component which is present in the nanoemulsion formulation. So here is the main important perspective of my research that as we know based on some dilantin formulation, they have some side effects. So what I have done is I have done a quick experiment to see how the dilantin solution and emulsion is behaving when we show some uh, in vitro injection. So I prepared the dilantin solution with the same concentration as phenytoin and HIP emulsion with using 1.2 mg per mil and 12 mg per mil. And I have diluted this solution and emulsions using PBS 7.4 buffer at 1 to 10, 1 to 100, and 1 to 1000 dilution ratio. So dilantin solution at 1.2 mg per mil and 12 mg per mil shows that as I dilute the solution with the PBS 7.4, the pH of this solution is reducing from pH 10.4 to pH 8.3 and pH 7.3. And as I'm diluting, it shows it shows the birefringent particles in the microscope. So it can show that as diluting solution was diluting, it can precipitate the drug and it can cause that side effect. However, in phenytoin and HIP emulsion, when I dilute the emulsion with the PBS buffer, it shows the pH around pH 7.4. However, there is no birefringent particle were observed. That means the drug is mostly trying to stay into the oil phase, and it's not transitioning from oil to aqueous phase and precipitating out. I did this experiment at 30 minutes and 4 hours, and still it was showing the same results. So based on this data, it shows that by incorporating drug into the oil phase, we can prevent the phlebitis type of issue of that BCS class 2 drug. And however, with the using the HIP emulsion like iron pair complex, we can enhance the drug loading 10 times higher than the actual molecule. Here is the next in vitro release study of this molecule with the iron pair complex. The study design is that the same amount of phenytoin and compared to HIP complex was dissolved in 1 gram of castor oil each. 0.5 gram of this oil was placed in this flow through cell. So for in vitro release study, I have used this USP apparatus 4, and I have used this flow through cell. This cell is basically for suppository purpose, but however, the main purpose is that uh, that oil depot could be stay on the top of this cell. So when the dissolution media pass from bottom, uh, and then it's going to the top and then contacting the surface of this oil depot and releasing the drug slowly, and then collecting the samples from the other side. The flow rate of this dissolution media is very low, around 0.1 mil per minute, so that it cannot disturb the oil depot. And samples were collected every 12 hours for 7 days. So here is the in vitro release profile at PS 7.4. And this profile shows that uh, around 7 days, the phenytoin has a 100% dissolution or 100% drug release. However, with the HIP, we can reduce the drug release from, like I would say, 40% lower with around 60% of drug release 7 days. So that means like by incorporating drug into the iron pair, we can modify the drug release of this phenytoin type of molecule, and we can modify the drug release and also use in a long-acting therapeutics formulations. So in summary, I would say iron pairing is a really good technique which can help to reduce the melting point. It can enhance the oil solubility, and because of high log P value, it can also enhance the lipophilicity using iron pair technique. Also, the other thing is by incorporating drug into the oily phase, we can reduce or prevent the in vitro precipitation of the drug. And by using the iron pair technique, we can have 10 times higher drug loading can be achieved into the phenytoin type of molecule. And the third perspective was that iron pair could be used to long-acting therapeutics to control the release of the drug. So thank you, everybody, for listening my presentation. Any questions?